Hello and welcome back to sections 18.1 through 18.5. In this video we'll be using example 2 to demonstrate how to handle work due to a moment. So we have an applied moment of 100 foot-pounds right here. So it's going this way. We're asked to figure out what omega 2 is. So in this bar, state 1 is right here, and then state 2 is up here. So we want to know what omega 2 is when the bar gets up here. Alright, so let's look at the sheet I have over here. So I've redrawn the problem. Make that a little brighter for you guys. So we have the same thing. We have a fixed point O. I have drawn state 1 down here as a solid line. So the center of gravity is at the center of the bar. I have 50 pounds going down, and then I have this 100 foot-pounds acting. I have state 2, so I've decided to combine them at point O because point O is fixed. So a good idea is to have your state diagrams. So I have state 1 here and state 2 over here. The bar is 5 feet long, but I've only labeled 2.5 feet to the center of gravity. Alright. So to get started, we're going to use conservation of energy. So that equation is sum of T1, which is kinetic energy at state 1, plus sum of V1, which is potential energy at state 1, plus sum of the work not conserved, so the work from state 1 to state 2 that isn't conserved. So again, this is forces or moments that cause us to move in the direction of that force or moment are positive. If they cause us to, basically if we move opposite, then it's negative. Equal to the kinetic energy at T2, so this is where our omega 2 will reside. It'll be in that variable. And then sum of the potential energy at state 2. So before we solve this, I'm just going to take a quick tangent. So for V2, this is composed of springs and gravitational potential energy. So we will have gravitational potential in here, but there are no springs, so I can't really show you, but I do want you to know the equation. So we've already seen linear springs being 1/2 k delta S squared, but there's also not going to be torsional springs. So torsional springs being things like mouse traps, where they introduce a moment as you rotate them. So if you ever needed that equation, VE, so this is for torsion, it would be 1/2 k, and so this k will be different units if it's for a torsion spring, and then theta squared, where this theta is in radians. Okay, so that's the other equation that you might need in your homework. All right, so let's go through here and solve our conservation of energy equation. So T1 is kinetic energy at state 1. So we start at rest, which means that this is 0. We don't have any velocities, we don't have any angular velocities, so we don't have any initial kinetic energy. V1, I already stated we don't have any springs, so this is just gravitational potential energy. So you can look at this two ways. So you could put the datum here at G1, and then you just shift your potential energy over to V2. Or you can say the datum's up here, and then you have a negative potential energy here. So that's what I'm going to do in this case. I'm just going to call this line up here my datum, and therefore we're going to be 2.5 feet underneath of this. So V1 is going to be weight times delta height. So our weight is 50 pounds, and our delta H in this case is going to be negative 2.5 because we are underneath. Remember, for weight, we assume that that up is positive. So a positive y will give us positive potential energy, so we have a negative. We're going underneath the datum. So negative 2.5, which will give us a total of negative 125 joules. Okay. The next term is the sum of the work from 1 to 2, non-conserved. So a lot of times this zeroes out, but let me get my mouse out of the way for you guys. But for this problem, we have this moment up here, and that is going to introduce work due to a force, or in this case, work due to a moment. So we're going to have the integral of the moment d theta. Now, it's true that this force is also producing a moment, but we've already accounted for this force due to gravity in our potential energy equation, so I do not need to include it down here as well. It's already taken care of in this part. So our moment is 100 pound-feet, so d theta, so it's just 100. And then this is a positive 100 because it acts this direction, and our bar rotates in the same direction, so it acts in the same direction as the body will be moving. So therefore it is a positive work. We're going to go from 0 to 90, again, following the positive sense that we've already defined here. So when we solve that, we will get 100 theta from 90 to 0. We don't want to actually use 90. We want to turn this into radians, so that is pi over 2. So then we get our pi over 2 to 0 down here. So we get 100 pi over 2, which is 50 pi. And I could convert that to a number, but we don't really need to for right now. So we're just collecting all of our terms. We're just going left to right. So the next term is T2. So there's only one body here, so there won't be any sum ofs. So our T2, so we could write this as the 1/2 velocity, 1/2 mass velocity squared plus 1/2 I omega squared. But we've already established that we have a fixed point about O here. So that's an instantaneous center. It's a fixed point O, whatever you want to think of it as. It's basically a point with 0 velocity. So I can use the shorter method as you saw with example 1. So I can write this as 1/2 I naught omega squared. So then we get 1/2. The I naught will then be this x prime term, because the x prime is about the endpoint where this is about the center of gravity. So I'm going to use the 1/3 ml squared here. And then don't forget our omega squared. And then we fill in our numbers, and we'll solve. So 1/2 and 1/3 will become a 1/6. Our mass is 50 divided by 32.2. Don't forget that pounds is not a mass. L is 5 feet, not 2.5 feet. Make sure you square that. And our omega is what we're trying to find, so we're going to just leave that as omega. And then when we solve that, we will get 6.470 omega squared. So just kind of clean it up before I put it all back together. Alright. And then the last piece is our V2 term. So if we look at this, our gravity is here on the datum, so our delta y will be 0. So therefore our V2 will 0 out. So one of these v's will 0 out depending on where you put your datum. So now we can just put all of our numbers together. So we're going to bring our equation back down. So we're going to get 0 minus 125 plus 50 pi equal to 6.470 omega squared. And then I'll go ahead and put the plus 0 from this, just so you know where everything's coming from. You solve this for omega, and you will get 2.227 positive radians per second, which means that it will rotate like this. Alright. If you have any questions, feel free to reach out.